Okay, so we're recording now. So we had a suggestion that we could start with a little recap of the SN1 reaction first, and then we can move on to talk about problems or maybe homework or whatever you guys have in mind. So if that's okay with you, I'm gonna start sharing the screen so we can look at the overheads, and we can talk about the SN1. So I don't know if this is something that you guys have had enough time to think about yet, but the really important part about this chapter is to make sure that everybody's filling out their worksheet. There's the worksheet. And that you're making fairly obvious that there's a difference between SN1 and SN2 reactions. And the main difference is when do you use SN1 and when do you use SN2, right? So the other day when we talked about SN2, we made a big deal about what is the best substrate for that reaction, right? And we justified what was the best substrate for SN2 by explaining that the nucleophile has to get to the active site for that reaction to get started. So do you guys remember what was the best or most likely substrate for the SN2 reaction? What were we looking for there? Methyl, primary, secondary, what was best?
Methyl.
Methyl was best, right? Because it's super easy to get to the back of it, to the active site. And then after methyl, we said primary would be our next choice, right? Still a lot of access to the active site. Then secondary, things were starting to get a little dicey. It was a little bit harder to get to a secondary site, and it would be nearly impossible to get to a tertiary site from the back. Now, the SN1 reaction is completely different from SN2 in that the mechanism is different, right? You don't need to attack the backside of the molecule in an SN1 reaction. What you need to do is you need to make a carbocation. That is the most important part of that mechanism, okay? And we know, because we've talked about carbocations a lot in chapter 4, that if you want to make a good carbocation, what is the best thing that you can have around the carbon that has a carbocation? Lots of what? Lots of carbon neighbors, right? So in the SN1 reaction, as you can see here in this arrow, the reactivity is opposite the one that we had for SN2, in that the best possible substrate is a tertiary carbocation. Got that? Then secondary, then primary, then methyl, okay? And if we look at the mechanism of the reaction, you will see why that is. So here's the mechanism that I gave you for the SN1 reaction. I think you may have had a chance to look at it. And you may notice that in this mechanism, the most important part is forming this carbocation over here. Okay, the nucleophile doesn't even come into play until you have already made that carbocation. Got that? So if we are going to be looking for a carbocation as the most important part, then it makes sense that the carbocation, the tertiary one, is going to be the best possible substrate.
Hey, Kelly.
Is that correlation making sense for you guys?
Kelly, you might need to mute your mic. I'm hearing like a lot of feedback.
Okay. So,
yeah, that makes sense.
So let's see. Why don't we go step by step in this mechanism, right? Because I'm sure that you guys are going to have some questions about it. Let's do the mechanism one step at a time. And then we can make sure that we fill our worksheet so that we have the same information for the SN1 reaction as we had for SN2, so you can use that to make choices between the two of them, okay? So the mechanism in this particular case that you have here, as you can see, your leaving group is an OH group, okay? The thing that we're trying to replace, the thing that we're trying to substitute is this OH. And the OH has to go in order for somebody else to come in here. However, we talked about what good leaving groups are and bad leaving groups are last time. You guys remember that? And we said that OH was not a very good living group. And the reason why it's not a very good living group is because OH is strongly negative, right? And it's very attracted to this carbon. Oxygen is fairly electronegative. And this is a really close bond, and it's really hard to get rid of OH. So if you were expecting OH to just walk away, that's never going to happen, okay? OH is not the kind of living group that just leaves. Something needs to be done to convince that OH to go. And what we can do to convince that OH to go is to find us a nucleophile that comes like this HBr in the form of an acid. See the HBr here? You could also use something like HCl. We will talk about other nucleophiles in a minute, okay? The important part is if your nucleophile has a hydrogen attached to it and the OH likes hydrogen, the oxygen in the OH has 2 lone electron pairs. Those are going to be strongly attracted to positive things like protons that might be floating around. If you can protonate your OH, you now have turned it here into water. You see the red water in this picture here? Water is a good living group. OH is a bad living group. So what you have done is you have turned OH from a bad living group, you have protonated it, and you have turned it into a good living group. Got that? Now that we've done that, the water is willing to leave, and it does. It just takes the electron pair and goes away. And as a result, we make a carbocation intermediary right here. A carbocation intermediary has a positive charge on it. This carbocation that we made here is a very nice one. It's a tertiary carbocation. So the central carbon is completely surrounded by carbon. It's very stable. And then the bromine that is floating around that came from this step, look, this bromine wasn't doing anything until now. Now the bromine can come in and it can attack that carbocation. And that's how you get to your product, okay? So the most important step in this reaction, the step that determines the speed at which this reaction can go, is making this carbocation. If you can make a good carbocation, your reaction is going to go fast. If you cannot make a good carbocation, your reaction is going to go slow. Does that make sense? More or less? Thumbs up or something, some kind of gesture. Thank you, guys. That's very nice. Thank you for giving me feedback. So let me go back here for a second and then we'll look at the stereochemistry. This is your carbocation here, and the carbocation is being attacked by the bromine. So what we're going to look at in the next overhead is what does a carbocation look like if we were to make a model of it. So here is an intermediary for the SN1 reaction. We started with a substrate that was chiral, just to show you what might happen to it. You remember what chiral means, right? 4 different substituents attached to the carbon in the middle. And what we have done is we have taken away the leaving group, okay? So the leaving group went away, and when you take away your leaving group, a carbocation is actually flat. It is planar, okay? Here's your carbocation after we took away the leaving group. Here's the positive charge. We put the positive charge here, but you have to remember a positive charge is an empty p orbital, and an empty p orbital can be attacked from either side. So carbocation intermediates are flat, and or what we call planar, and they can be attacked from either side. And that means if you spend the money to buy a chiral substrate here in the beginning, once this reaction is completed, if you start with something that was R, you're going to end up with a mixture of R and S. And if you start with something that is S, you're still going to end up with a mixture that is 50-50 R and S. So what that means is you can depend on an SN1 reaction to keep the stereochemistry of your product, okay? This is in contrast with the SN2 reaction. In SN2, if you start with S, you end up with R. And if you start with R, you end up with S. Very reliable inversion of the configuration. Here, you do not retain the configuration. You get a mixture of R and S when your reaction is completed. Does that make sense? More or less? Okay, let me stop sharing the screen for a second just to check the chat and make sure that we're answering all your questions. Grant had a question. Is exam 3 still next Thursday? Yes, Grant, it still is. And what that means is the material that I'm going to post for you guys today is going to be the last material that's going to cover on that exam, okay? So today there's going to be a video posted this afternoon about elimination reactions, and that's going to be the last stuff that is going to be covered for exam 3. So I don't know if Grant can hear me, so I'm going to type that here just in case. Yes, exam 3 is on Thursday. And just so you know, the exam is going to be deployed during the regular class time. You will have 3 hours to complete it. If the regular class time does not work for you, I need you to let me know so we can make other arrangements. But that's the idea. Everybody starts to take the exam at the beginning of class time, and you have 3 hours to complete it, okay? Do we have any other exam questions that we should talk about before we move forward?
I was just wondering, this isn't about the exam, but it's about the final lab quiz. But if you want to answer it later, we can talk about it later too.
You can tell me, Sia, what's your question about the lab quiz?
I was just wondering, like, the time limit for it, and like if it's going to be the lab hours, or what it just, yeah.
Yeah, your TAs have been told to administer the lab quiz during lab time. The lab quiz is written to be about a 30-minute quiz, but we're giving you the whole entire lab period to complete it. So you will get your lab quiz via email, and you're supposed to return it to your TA by the end of that lab. Okay? So the labs are 2 hours and 55 minutes. That's the time that you have to complete that quiz, which is plenty of time. We have, we actually already did quizzes for the second semester organic lab, and we didn't have any problems with time, and it was a fairly safe delivery method.
Okay, sounds good, thank you.
If anybody cannot, for whatever reason, if you have to work, if you have childcare responsibilities, whatever, and the lab time does not work for you, this would be a good time to contact your TA and let them know that you need a different time. Okay, we're making all the accommodations we can make to make sure everybody gets their lab quiz done. Any other questions about the exam or the, okay, James has a question. How much does the lab final count for the final grade? The lab final is 1/6 of your final grade. So your 5 lab report grades and the lab final grade, they're all average. You have 5 lab reports and 1 lab final, so it counts for 1/6 of your final grade. Most people do fairly well on the lab final, and they tend to keep the grades that they have in the lab, but don't underestimate the lab final because it can bring your grade down if you don't put some time into it, okay? So if you haven't received the study guide for your lab final, or if you don't know what's going to be on the lab final, let me know, because your TA should have communicated with you about that.
I have not received a study guide yet.
Okay, so if you want to send me an email with your lab section number, I'll take care of that.
Okay, thanks.
Okay? And that goes for anybody who hasn't received information from the lab TA. Other questions before we go back to the overheads? Not for now? Okay. So, next thing I wanted to talk to you about was the living group, okay? Living groups are still very important in the SN1 reaction. If your living group does not want to leave, you're gonna be unable to complete your reaction. So you can see how that's gonna be very important. The best living groups are those that give the most stable anions. That's another way of saying, if you have something that is very, very electronegative, that's gonna be a bad living group, okay? OH and fluorine are two of the worst leaving groups that you could possibly have. Fluorine didn't make the cut in this picture, but if you were to put fluorine in this picture, it would be right next to OH. OH and fluorine are terrible, terrible leaving groups, okay? Why is that? The bond between them on carbon is a very strong bond, and they don't make very stable anions when they leave, so they're not very good leaving groups. As you can see, the order that we follow here is the same order that we follow for the SN2 reaction. Chlorine is a slightly better leaving group, bromine is much better, iodine is much, much better. And when you give OH a proton and you turn it into water, as you can see, water is a really good leaving group. See where water ends up? It's just as good as if you had iodine. So it's an excellent leaving group. And that's the idea of the mechanism that I showed you. If you start with OH, which is a bad leaving group, you can turn it into a good leaving group by protonating it, okay? So I think that it would be a good idea for us to spend a little bit of time filling up our worksheet with information about the SN1 reaction. And we can use our whiteboard for that. And you guys can help me and remind me what were the things that we wrote in our previous worksheet to make sure that we have more or less the same kind of information. And I think I recall that we divided our screen in half, right? Because here on this side, we talked about best substrates. And on this side, we talked about best nucleophiles. I don't know if you remember that. But we're gonna try to do the same thing here so that everybody can have that information when it comes time to fill in the worksheets. Are you guys having trouble filling those worksheets, or do we know what kind of information goes in there? Okay, I see one thumbs up. I appreciate that, Caitlin. I hope everybody else is also filling them up. Okay, so the best substrate, and this is for the SN1 reaction. So let's make sure that we put that up here. SN1 reaction. This is the part of the worksheet that we're filling today, okay? It's the SN1 reaction, and we're gonna start with the best substrate. So what should I say here? What should I say is the best substrate? Is it primary, secondary, tertiary? What is the best one that I could have?
Tertiary.
Tertiary is the best, right? Because, let's put a justification here, it makes the most stable carbocation intermediate. I feel that that will help you guys remember when you're taking the test that the intermediary in this reaction has to be a carbocation. And then after tertiary, who comes next? Not as good as tertiary, but still decent.
Secondary.
Secondary, right? Capitalize that. A secondary substrate. And then after secondary?
Primary.
Primary. And then the worst possible substrate for this reaction would be a methyl substrate, okay? So this is tertiary up here would be the best, and methyl down here would be the worst. Does that make sense? And we're going, I think you can draw an arrow. So we're going from best to worst. And there will be questions on the exam about ranking things according to who's the best substrate for this reaction, which one is the worst, just like there was in the homework, okay? And in the suggested problems. So make sure that you have that information handy because we're going to need it, okay? Now, does anybody have their worksheet around that we were filling up last time with the SN1 and SN2 reactions? Does anybody want to tell me what other information might we want to put in here?
The leaving group reactivity.
The leaving group reactivity. So the leaving group reactivity is identical for SN1 and SN2, Nicole. So whatever you had for SN2, as far as living groups go, it still applies here, okay? The living group is the only thing, the living group reactivity is the only thing that's not going to be different between these two reactions. A living group is a good living group. A bad living group is a bad living group. That's not going to change, okay?
Okay.
Say that again.
Okay.
Okay. If I recall correctly, we talked a little bit about nucleophiles, right? What kind of nucleophile can you use in an SN2 reaction? Do you guys remember what kind of nucleophiles we use for SN2?
Salt.
Salts, right? And can you give me an example of a salt that we use?
NaCl.
We could use NaCl. We could also use KCl, right? Remember, all the sodium salts are good. We can also use potassium salts. In this case, in the SN2 reaction, instead of using salts, we're going to use the acid form of the nucleophile. So for example, if in the SN2 reaction we use sodium chloride, we probably want to use HCl here, hydrochloric acid, okay? If you use sodium or potassium bromide, you probably want to use HBr here. You can use HI to deliver iodine as your nucleophile instead of NaI or Ki, like you did in lab number 5. Other acids that we use sometimes for the SN1 reaction are things like HCN, which is hydrogen cyanide. Again, hydrogen cyanide is super, super poisonous, but we're online, so we can safely use that for our reactions, right? Nobody's gonna get poisoned. And sometimes the SN1 reaction uses water as a nucleophile in the form of H2O. So H2O is a nucleophile that can be used in the SN1 reaction. And you guys remember those fancy solvents that we use for the SN2 reaction? We talked about them a little bit. We had solvents like acetone and DMSO, remember that? The most common solvent for the SN2 reaction is actually water. No fancy solvents like acetone and DMSO. We use acetone and DMSO when we were doing the SN2 reaction because we wanted solvents that didn't have protons available. We wanted what is called an A product solvent. In this reaction in SN1, we're okay having product solvents. We need protons for this reaction to go, so we're okay with using water. Sometimes we also use alcohols as solvents for this reaction, and that's okay. You can use alcohols. They have protons. They're fine solvents to use in this particular case, okay? If anybody has their worksheet handy, did we write any other things about the SN2 reaction that maybe we want to clarify about SN1? Is that all we wrote? I was curious about whether we wrote anything in our worksheet about stereochemistry for the SN2 reaction. Did we write that if you start with S, you end up with R, and if you start with R, you end up with S? No? Maybe we should. Maybe we should write that there, right? So that was true for the SN2 reaction. For the SN1 reaction, you cannot predict the stereochemistry of the product. Okay, you get mixtures of R and S products if you start with chiral substrates. What that means is can't keep or invert stereochemistry. You can't expect, it's the real word that should be here. You can't expect to keep or to invert the stereochemistry. You don't know what's going to happen to it. You know that you're going to get a mixture of products because your carbocation can be attacked from either side. So there's no real way to predict what your final stereochemistry is going to be. Okay? So that gives us a pretty good idea of what we should put on our worksheet as far as the SN1 reaction is concerned. What kind of questions could be on the exam about the SN1 reaction? You could be asked to do the mechanism for an SN1 reaction. That would not be a difficult question, I don't think. You have the mechanism, you can apply it here. You may be asked to choose from a list of reagents which one would react fastest in an SN1 reaction, like in the question that is in the homework. You could be asked to decide if a reaction is going to go through an SN1 mechanism or an SN2 mechanism, depending on the conditions that we give you. And in order to do that, you will have to check the nucleophiles, you will have to check the solvent, and you will have to check the substrates. All of those things are going to help you make a decision. Okay? We got that? Okay. I'm going to stop sharing for a second just to make sure that I don't miss anything. Can you turn any other bad leaving groups into good ones besides OH? Taylor, that's a very good question. I don't know if everybody can see that question on the chat. Can you turn any other bad leaving groups into good ones besides OH? Not in this class. Of the leaving groups that we know in this class, the only one that can be turned from bad to good is the OH, the hydroxyl leaving group, okay? For example, if you have fluorine as your leaving group, and fluorine is a terrible leaving group, there's no way to turn fluorine into a good boy by offering a proton. Fluorine is not interested in grabbing your protons, okay? So that's not going to work. The only one that goes from bad to good is the OH leaving group. And that's a good question. Other questions that we might answer on the chat, or you can tell me what you're thinking of. No questions? How are the homework questions coming along? Did everybody get those done?
Yes.
No difficulty there?
No problems.
No problems? Okay.
I had a question about the very first question on like the second homework.
Uh-huh.
And so like when you're looking at like the order of SN1 reactivity, the reason that I picked, I mean, I got it right to start with, but I just want to clarify to make sure that the reason I got it right was due to, it says it's in descending order, so that would mean it would go in the left or right. And there, it looks like the carbon is tertiary and it has 3 neighbors.
Mm-hmm.
So that would,
yes.
so that would mean it's very reactive and not less reactive, correct?
That's correct.
Okay, so that.
What we could do, Justice, let me put that question on the screen so we can all be looking at the same thing in case somebody has not had a chance to look at it or review it. Can you all see the question now? The order of SN1 reactivity for those alkyl halides. So the question is are they listed in decreasing order? And that would mean, decreasing order would mean what?
Lowest to highest.
So decreasing order would mean highest to lowest. The best one should be first and the worst one should be last, okay?
Okay.
So this guy that you have here, the first one here, I'm trying to avoid the little red dot to appear. The terbutyl chloride that you have there in the first, as your first compound, right there, that is actually the best possible reagent for this reaction, right? It's tertiary. You see how the chlorine is attached to a tertiary carbon?
Yeah.
That would be a great place to start if we're going to list them in decreasing order, going from best to worst. This guy is the best. The question is, the one that's next to it, is that the second best? And I'm talking about, ooh, I wish I could make this little thing go away. I'm talking about this guy right here that my cursor is sitting on right now. What kind of substrate would that be? You have a carbon that has 3 hydrogens attached to it. Do you recognize what we call that?
A methyl.
Methyl group.
That's a methyl group. And the methyl group, if you go back to the stuff that we just put in the worksheet, is it a good substrate for SN1 or a bad substrate for SN1?
Bad.
Bad.
Bad, really bad, okay? Why is it so bad? Imagine trying to make a carbocation that doesn't have any neighbors. Wouldn't that be terribly bad? Yes, I'm answering my own questions at this point. I don't even care. So the order in which these guys are listed here is incorrect. The first one, which is the terbutyl chloride, the one that is covered with the red, which I'm gonna move away from now, is the best substrate. For the second one after it, which is this methyl group, is not the second best substrate. Does that make sense, Justice?
Yes.
If I had to move this little methyl group and put it in the right place, where would it go?
Towards the end.
It will go at the very end, because that's the worst one, okay?
Okay.
You know what we could do? Let's go back to the whiteboard, and we will put those substituents that we have there in order, in the order in which they should be, okay? So let's, and this is gonna be a drawing, so please forgive me if it looks a little clunky. We're still talking about problem number 1, and we're ranking those substrates in the order in which they would go in an SN1 reaction. So the first one that you had there was this guy, right? Oh, that's not bad. Look at me, I'm getting better. If that was the one of the choices, would that be a good substrate for SN1 or a bad substrate for SN1?
Good.
Good.
Be really good, right? So let's put a text box next to it, and we're gonna call this guy our best substrate. Is that good? Now, of the things that were listed there, the methyl one was the worst. So I'm gonna put it down here, okay? I'm gonna draw it down here. And actually, I can just type that one because it's CH3Cl, okay? If we were ranking substrates, what would this guy be? Best, second best, third best, or worst?
Worst.
That would be our worst substrate, right? And in between, I do believe that we had, let me go check and see. We had isopropyl chloride and ethyl chloride were the other choices. So let's draw them in here and make sure we put them in the right place. Isopropyl chloride looks like this. No, I don't want that. I want to draw a picture, okay? More or less. That was isopropyl chloride, right? And then the last one was ethyl chloride, which looks like that. So if you're going from best to worst, this is the order in which you should list them there. Does that make sense, Justice?
Yes, ma'am.
And that's not the order in which they were listed in that question, right?
Yes, ma'am.
So that's why false was the correct answer. Everybody got that? Okay. Other questions that we should be taking a look at. I think we're reaching the point where everybody's just zoomed out and just wants the meeting to be over, but we still have time to answer any questions that you guys might have.
So I have yet to copy some of the mechanisms of the SN1 reaction onto my worksheet. And the only one, well, there was one in the, what is it called, in your video. Should I just copy that one or go look for different ones? Or is there the chance that we could practice one?
That's a good question, Christine. So you can definitely copy the one that I gave you in the video, which is the same one that's in the overheads that are posted on Moodle, right? If you look at the scan of the book that I sent to you guys, you will see that there is one in there that has a different leaving group. it has chlorine, I think, or bromine as the living group. You could copy that one as well, right?
Okay.
Just to make sure that you know how to do either one. And then on the suggested problems, there are going to be some other ones that you can practice with. I mean, the really important thing about the SN1 mechanism, just like SN2, they always go through the same steps, right? So if I'm giving you the mechanism with terbutanol, which is the one that I gave you, or terbutyl chloride, which is the one that's in the book, the important thing is, if I gave you a different compound, could you do it there? Is that making sense, Christine? Could you apply the same principles of that mechanism to a different compound?
Yes, ma'am, it does. It does.
Let me open the sample problems since we have time to do that, because I don't know if you guys have had enough chance to look at it, but there are some suggested problems from chapter 7. And if you open those, you will see that, and let me put that on the share screen so everybody can see them. Here they are. Okay, so everybody should be able to look at the suggested problems now. You will see, Christine, that there are some naming problems, right? Naming haloalkanes. Those are the easy ones. That's a softball. That's from chapter 2. And then there are some problems that are increasingly more complex. One that we should definitely be paying attention to is something like 719, which is a problem where they're giving you the condition. 719B would be one that I would recommend that we look at, for example. They're giving you the conditions for this reaction, and they're asking you, what kind of reaction was this? We haven't covered this reaction yet, but it will be in the video that you're going to do this afternoon. So you're going to be able to answer questions like that. Let me go to the next page here. Here we go. Here we go. So a question like 738 could also be interesting. They give you a substrate, 1-bromopropane, and they give you some different reagents, and they ask you what happens when you do these different reactions, okay? So if you look at these nucleophiles here, sodium iodine, sodium cyanide, that should be giving you an indication that you're doing an SN2 kind of reaction, okay? So that's another example of the kind of problems that we could ask you. And in general, you have a lot of problems here that ask you to put things in order of reactivity, ask you to put things into which one is a better living group. So a lot of the questions that are going to be in the exam from chapter 7 are going to be questions similar to the ones that are in the homework, where they ask you to put some things in order of who is more or less reactive, or they ask you to decide what kind of reaction you're trying to do. Does that put your mind at ease a little bit about the kind of things you should expect?
Yes, thank you. And you said the first one you said was 718 or not 718, 719?
719B
Okay, 719.
was one that's going to be important for us.
Okay, awesome. Thank you.
I'm going to go through the suggested problems that are on Moodle, and I'm going to take the ones that we won't cover because we're not going to get to the very end of the chapter, just so you know. So that's going to make your life a tiny little bit easier, okay?
Thank you.
Okay, and let me stop sharing the screen to see if there are any other questions in the chat or anywhere else. Anybody else got any questions, concerns? Anybody has some good news they can share with us? Even remotely good news are appreciated at this point. Like literally, if you got out of bed and put pants on, we'll take that. It's almost Friday, that's true. Except that Saturdays and Sundays look suspiciously like the rest of the week right now.
I was gonna say, does Friday even mean anything right now for like those of us?
No, it's just a day. It's just another day. I really try to not do work on Saturday and Sunday, but I end up having to work anyway. So really, there's very little difference.
It just means that more people are at the parks on the weekends.
Yes, so you should stay away from them.
Yeah.
True. I saw the scariest animation today showing how when somebody is running or biking in front of you, if they're breathing hard, those particles are like literally hitting you in the face. So I will never walk or bike behind anybody else.
Mom just sent me that.
Yeah, isn't it super scary? It's
It's gross.
it's really gross. Yeah, like I will never run behind anybody else, not even my own kids. And Justice says no corona this way, which is always good news. That's very true. We have been relatively lucky in North Carolina, that's for sure. Any other questions? No? Okay. Well, if there are no more questions, you guys, I'm going to stop recording and